All right, so let's take a look at a couple examples on how to draw some of these shear and moment diagrams. This first one, I have a 20-foot long beam, 25-foot long beam, 20 foot between the two supports with a 3 kip load on the end. We want to draw the shear and moment diagram. So step one is to solve for your reactions. And here I would have a reaction at A and a reaction at B. And I would sum the moments about A and set it equal to 0. By times 20 minus 3 times 25 is equal to 0. So that gives me a reaction at B that's equal to 3.75. And then from sum of the forces in the y direction equals 0, I have AY plus 3.75 minus 3 is equal to 0, or AY is equal to negative 0.75, pointing down. So the first step that I do is I draw those lines, those reference lines, and I would have one at each one of these, supports, one at each load. In this case, there's just one at the end of the load. And then let's start by looking at our shear force, V. So I'm going to label it V. Units in this case are kips, K. And the way that I do this is, let me draw in these actual reactions. So it's going down 0.75 and BY is going up 3.75. So what I would do is I'd look at the direction on my shear and I say, oh, that's how far I go down. So I go down 0.75 and then nothing happens as I move over till I get to this reaction. It should be a straight line. When we get to this point load, it says go up 3.75. So this is actually negative 0.75 plus 3.75 brings me up to 3. You go over, and then it says go down 3, so I go down, bringing it to 0. Now the next step that I would do is probably find the areas. So what I have is negative 0.75 times 20 gives me negative 15 for the area of that rectangle. And the other one is 3 times 5, or positive 15. So then moving on to our moment. Once again, putting in our units. In this case, it's kip feet. What I have is I look at the very end and say, is there a moment on the end? There's not, so I'm starting at 0. And I change by the areas in my shear diagram. In this case, I'm going down to negative 15. And then I say, well, how do I get from this point 0 down to negative 15? If this is a flat line, then I have a line with a constant slope. And same idea up here. I have a flat line. I have to increase by a positive 15, bringing me to 0. So I get something that looks like that. All right, let's take a look at another example. All right, so for this example, what we have is a cantilevered beam, two 5-meter spans, and a distributed load of 10 kilonewtons per meter on the second half. So this is really stepping it up a level, much different than what we've seen before. To start off with, we want to find the reactions. Now this is a cantilevered beam, which means I could have a moment over here, and I could also have a point load. So I'll call this AY and the moment at A. I could put AX, but it's going to be equal to 0 from some of the forces in the X direction equals 0. So I'll skip that part. So what I'd probably start with is some of the moments about part A is equal to 0. And remember, if we're doing moments, and there is actually a moment I included in the calculation, so the moment at A minus, we can take this 10 kilonewtons and replace it with a point load, so that's 10 times 5, or 50 kilonewtons, and that'd be acting at 2.5 meters away from that point C. Or I could say that I have a moment of 50 kilonewtons times, what would that be, 7.5 equals 0. So the moment at the end at point A is 375 kilonewton meters. And from some of the forces in the y direction equals 0, I have AY minus 50 is equal to 0, or AY is equal to 50 kilonewtons. So after I have my my reactions, I want to draw those lines where anything looks like it might be interesting, which is like at the end, right where the distributed load starts, where the distributed load ends, and going to start here by drawing our shear diagram V. Don't forget to put your units on here. These are in kilonewtons. And we're starting off with this AY at the end of 50. So we just have something that starts right over here at 50, and the moment doesn't have any impact on the shear. And I get over to this point. Now I have this distributed load. Now when I'm doing the moment diagram, I'm looking at the areas now, right? So the area in here is 50, and it's pointing down, so it's like negative 50. So if I start here at 50, I have to go down by negative 50, brings me to 0. And if this is a flat line, then this has to be a line with a constant slope, like that, right? Then I can find the areas under both of these. The area under the first rectangle is 50 times 5. And the area under the other one, 1/2 the base times the height, is 1/2 times 5 times 10. So after we have the shear, then we can move down to the moment diagram. And the moment diagram units will be kilonewton meters. Probably the hardest part is how do we treat this external moment at the end? In this case, the moment is 375, and say, is that positive or is this a negative moment? And I have to say, well, what would it do to the beam? Would it make it want to frown or smile? And you could take your thumb and try and push down on that, and hopefully you could see that it would make it want to frown. So I would start off with a negative 375 kilonewton meters on the end. Then I change by the magnitude of the area in my shear diagram, which is a positive 250. So 375, negative 375, and then we're going to go to 120, negative 125. Because this is a flat line, then this has to be a line with a constant slope. And then for this other half, the area is 125, so 125, and it's positive. That brings me to 0. And then if I think about what the overall shape looks like, if it's down here, this is 0 slope. This like distance right here represents slope. So we're getting a higher and higher positive slope, which means it would look something like this. So those are 2 more examples of how to draw a shear and moment diagram. Hopefully those were helpful. Let me know if you have any other questions. Thanks. Bye.